As I said, I'm not going to draw beakers for you ever again. Well, maybe I will put them on. Cathode, reduction, anode, oxidation. Doesn't matter which type of cell we're talking about. The signs do change. There are the boundary phases. There's the double line for the salt bridge. That's mostly the way we connect things when we talk about problems. Or you can have an inert electrode. Then we started talking about electromotive force E cell, and I used the term volt. We measure cell potential in volts, or the voltage. What the heck is it then? I'll tell you. What the heck is that? J stands for joules. That's the energy term. C is the coulomb. On some of the old quizzes, that used to be the abbreviation, but on modern things, it's capital C, and you have to just take it from the context. But that's the unit of charge. One electron has a charge of minus 1.6. In the back of the book, they give you a few more significant figures. So each electron is minus 1.6 times 10 to the minus 19 coulombs of charge. Okay? Now, if you take a coulomb of electrons, enough electrons to make 1 coulomb, which is about 10 to the minus 5 moles. In other words, you get a coulomb of charge, you have to multiply this by the number of electrons. So it's basically the reciprocal, so the number of electrons. Minus 618. Who's whispering? Go outside and whisper. Unless you want to get up here and lecture and show them how much you know. Okay, coming back to this thing then. So it's that number of electrons. Did I get that? No, 10 to the 18th. How can you have 10 to the minus 18th electrons, right? You can't have less than 1 electron, 10 to the minus 18th, because you have a really small fraction of electrons. So all I do is take the reciprocal. So that's how many electrons. And if we take that number of electrons plus, if we move that number of electrons in this direction, negatives repel. You have to do 1 joule of work to move that number of electrons through a potential difference of 1 volt. So these are just capacitor plates or something. You charge them up so that they have a 1 volt potential difference. Then you have to do a joule of work to move that number of electrons through that potential. Or if the electrons are moving in the other direction, they can do a joule of work. How would they do that? Lighting up your light bulbs. So that's what a joule. That's what the volt is. It's a joule per coulomb of charge. You have to do a joule of work per coulomb of charge. And you can get work out of the electrical cell. That's why you do that. You can play your stereophones or whatever you want to do with it. Okay? Then we talked about, what else do I have to talk about? I talked about, I set this up. Let's see if I have a next slide. There it is. There's my favorite cell. Zinc and copper, because it's cheap, we can set these up. Notice he's following the convention. He's written it on that side. That's reduction, oxidation. Okay? He puts this cell together, and you measure 1.03 volts. You can only measure potentials for a whole cell. That means you have to have an oxidation half cell and a reduction half cell. And then you measure a potential of 1.103 volts And you have to know which is the spontaneous reaction. How do you know what the spontaneous reaction is here? Well, one of the ways is, I said he followed his convention, so you know this is the reduction. Okay? But if I would have just given you some strange bunch of chemicals and said, I don't usually follow the conventions, how would you know? You wouldn't, unless I gave you a table of standard reduction potentials. Then you could calculate it. But until I do that, you can't. Or if I say this is the oxidation or that's the reduction, you know how to do it. Or if I say this is a galvanic cell and this is the positive terminal, when I say this is the positive terminal, it tells you it's equivalent to what? That you're having a reduction half reaction. Remember that little table I wrote for you? All of that stuff. So that's how you know all of this stuff. But right now I just said, I put this together and I measured that cell potential. Okay? You can only measure potentials for a whole cell. But you'd like to know something about this cell, and you'd like to know something about this cell. And so we make a reference cell. First of all, the potential between the electrodes. In other words, those two electrodes, there's a potential difference between them. Electrons going one way, you have to do work on them to move them. If they want to go in the other direction, the spontaneous direction, they do work. And by the way, he says these are really precise measurements. You can measure to 1 part in 4,000 or 5,000, even more possibly. That's hard to determine. But it picked an arbitrary zero. We call it the standard hydrogen electrode. We decided to call it SAT. Some of the more modern books call it NHE, which means normal hydrogen electrode instead of standard hydrogen electrode, because they don't want to be accused of doing sexism things, I guess. So anyhow, the standard hydrogen electrode is said to be zero by definition. He draws a picture of a standard hydrogen electrode. But when we're saying standard, we mean activity of 1, and that's about 1 molar. Notice you can't get an activity higher than 1. 1 is the maximum number you can get for activity, even though you can get 10 molar. We did that thing we were talking about pH scale. So far as we're concerned, we've calculated pH minus 1, but you know you can never go below 0. Yes?
What's activity?
Oh, remember I said that's one way of defining it, it's the effective concentration. At low concentrations, the activity number is close to the molarity number. At higher concentrations, obviously that can't be true, because we can have a 10 molar or 12 molar HCl, that's a stoichiometric number, and the activity for that is getting closer and closer to 1. And when you take physical chemistry, you'll learn how to relate activity and ionic strengths and all those things, which would be fun to do, but we don't have enough time this semester. So we're not going to do it. We're just going to make the approximation. And basically the way we handle that is just work at less than 0.1 molar for those solutions. Molarity and the activity are almost the same. And they get closer and closer as you go down. And if we're dealing with gases, pressure, let me push the button. There we go. For those, he tells you approximately what they are. And this is because this is from the older book where they didn't have the standard state defined to be 1 bar. And I don't think the problems have caught up, so they're still working at the old thing where they use pressures and atmospheres. So that's standard hydrogen electrode. And there it is. And the half reaction, 2 H pluses plus 2 electrons equals H2 gas. And I don't like the way he set it up that way. Looks Mickey Mouse to me, but anyway, you only do this once in your lifetime, and then you say, why will somebody else does it soon? Again, actually everybody's done all this, so you don't have to do whatever. But there are some different ways of doing the shorthand representation. I like the old-fashioned picture where here you have your beaker. You have HCl, and it's specifically HCl that you have to have in there, but it associates to give you hydrogen ion, activity 1. And so it's the maximum concentration you can get, and that's what it says over there. I'm going to fill my beaker a little forward. And you get a glass tubing. And the pressure as it comes out here is 1 bar because there's slightly water pressure. Then you have what is a little cup, little holes in it, of platinum. Now it's like the cap of this thing. It's all, and it looks black like that. You say, how come platinum's black? What they do is deposit a finely divided layer of platinum on top of the platinum metal. So the platinum metal conducts the electricity out of there. And this finely divided platinum surface gives you a really large surface area, and we could almost say the hydrogen gas dissolves in the platinum. So some books write this like this. And your book puts a bar here, and then H plus stays the same. So some books put a comma here because with that high surface area, it acts as a single phase. A mixture, a solution of hydrogen gas dissolved in the metal. So there's different points of view of how you want to write it. This is the way I'm used to writing it. This is the way your book writes it. I accept it. I'll do it that way. And of course, you put down activity as 1 or 1 mole. Okay? So that's the shorthand representation for that cell. Okay?
Is this a half cell?
This is only a half because I need to connect it to something.
Okay.
In other words, if I don't hook this up with a salt bridge, which I'll do in just a second, we'll let him do it. A salt bridge and all the other things, I only have half a cell, and I can talk about it, and I can bubble the hydrogen over this electrode forever at 1 bar. And guess what? There's nothing, no electrons are going to go anywhere. I'm just using up hydrogen. And watching and entertaining myself. Yeah, you can watch bubbles in the aquarium all day. Yes?
Is the genie ground or what's
No, gas.
gas? Okay.
1 bar gas.
Sometimes, you know, it's not wrong to do this either. Yeah, it's like 1 bar and you get rid of this parentheses. So different people have different ways of writing that short. What we have to remember is it's hydrogen gas, pressure 1 bar, H ion, activity 1, but it has to be specifically from HCl. You don't set these up with H2SO4 or anything else, even though you can adjust the hydrogen ion concentration to the activity of 1. It will be slightly different than the 4th or 5th significant figure, so it always is specifically HCl. Those are little things you don't have to worry about unless you're going to get into being an electrochemist and you have to set these things up and use it for your measurements all your life. So, I did it once. I don't have to do it again. Okay, moving on. Here's what we want to get to. I'm going to connect my standard hydrogen electrode to that copper. You can't quite see it. It's an activity of 1 again, or concentration of 1 molar. If that's what we're going to use, we're going to use molarity. So you got 1 molar copper here, and you got 1 mole of H plus. This is your standard hydrogen electrode. This is that porous plug or semi-permeable membrane. So you have an internal junction. If I wanted to write that down, shorthand. I would write this like this. I'm going to do what the book does, but I'll write this. There, 1 bar, dash. M, say activity 1. Another internal junction. So there's my cell. The metal electrodes are always at either end. That makes a whole cell. It's made up of 2 half cells. And he says, I measured E cell is 340 volts. What is the cell reaction? Or what are the 2 half reactions? Whichever. Anyhow, first thing I'll point out to you, you know what the spontaneous reaction is. If you put copper in HCl, what happened when you did it in Chem 2?
Bubbled.
Nothing happened. Put copper in HCl, nothing happened. Copper metal HCl. So, the potential reaction you could write this is what you could write, but you don't observe a reaction. That means the spontaneous reaction goes in this direction. No reaction with acid added to copper, so it must be spontaneous in the reverse direction. So the actual reaction would be, and you always rewrite equations, you don't do this, because what I always do is say yes, and I put an X. So I want you to rewrite it in the right direction. Okay. I don't want to look at it backwards. That means when I do that to you, you've written it backwards and I have to mark it wrong. And it says, there's one of my half reactions. Right? What's my other half reaction? I add them together and I get that for my spontaneous reaction. I'll draw a column here, D0 1/2. E0 cell we measure at 0.34 volts. Okay. This is what for the half cell? 0. I added these two. So I add these two and I get 0.34 plus 0 is 0.340. So far so good. Forget that negative up there, your cell, because all it says is you hook your cell up wrong and you always get positive numbers out of these things that are slow. Okay. So here, everybody knows if I take zinc, you get hydrogen gas. That's one where you got the hydrogen bubbles. Okay. So it's hydrogen gas plus plus. So I'm going to write that's my reduction half reaction. That's my oxidation half reaction. I add those together and sure enough I get the equation at the top. B0 cell is 0.763. If the hydrogen was 0 going in this direction, what's the hydrogen if you reverse it? 0. What's this one going to be? Because I add these two together, I added these two, this is what I get for E cell. Then you go to the table of standard reduction potentials for zinc, and you see minus 0.763. Why do you see minus 0.763? Go to my next slide. Zinc there. Not a zinc anywhere. Where the heck's my zinc? Oh, did I miss it?
No, they're there. The next slide.
Oh, there it is, right up top. Okay. He said minus 0.763. What's the difference? He's got a reduction half reaction. I have an oxidation. If I reverse this, what do I do to the sign of that? Change the sign. Okay. Now the thing we tabulate are standard reduction potentials. They're all referenced to the hydrogen as being 0. Okay? Except that I always make this joke. One of my fellow graduate students in the biochemistry department, he was a really bright guy. The biochemists don't know anything about chemistry. He wrote a textbook, and his textbook, which has sold millions of copies, I think they changed it once people started complaining too much. But his books always had tables of oxidation half-cell potentials. Because that's what they were interested in biochemistry. He sold lots of textbooks. He's probably playing golf, and I'm still here talking from his school. Anyhow, coming back to that thing, you can do oxidation half-cell potentials or reduction half-cell potentials. About 40, 50 years ago, somewhere about the time I started studying chemistry, that's why I could laugh at it, all the chemists decided to publish only tables of reduction half-cell potentials. So that's what we're working with. And it was just an arbitrary choice. They could have picked oxidation, but they picked reduction.